Hi everyone, I'm Jeff Liu. I'm the instructor for Remote Sensing for Disaster Response. The class introduces the students to geospatial information sciences, image processing, and deep learning for satellite and aerial imagery, network science, and decision-making in the context of emergency management. We feature guest speakers from industry, NGOs, academia, government, and international agencies, such as the World Health Organization and FEMA, to discuss real-world technologies, needs, and applications. For the final exercise, the students handle a simulated hurricane response where they have to predict impacts, coordinate evacuations, organize the distributions of resources to people in need, and conduct press conferences to keep the public informed on the state of the response. The students learn to make difficult decisions with incomplete information and must collaborate as a team to coordinate the many sources of information and tools available to them.
Hi everyone, welcome. I am Jeff Liu. As you saw in the last little clip, I'm the lead instructor. Very excited to present this year's Remote Sensing for Disaster Response. The name of the class really should be Remote Sensing and GIS and Image Processing and Optimization and AI and Machine Learning for Disaster Response, Relief, Recovery, and Planning, but we figured that was a little too long to include in the brochure. This year we featured over 20 guest presenters from research labs, international, federal, and state government agencies, nonprofits, and first responders to discuss the realities of how these technologies and methods are used in the real world. This would not have been possible without my excellent teaching staff, which I want to introduce, starting with my co-instructor, Katie.
Good morning, I'm Katie Piccioni. I'm an assistant staff at Lincoln Laboratory. My background is in remote sensing and disasters and also technology and policy. And it has been such a pleasure to work with the students the past month in the Beaver Works Summer Institute Remote Sensing for Disasters course.
Thanks, Katie. And our three TAs, starting off with Victoria.
Hi guys, I'm Victoria. I'm a sophomore at Cornell University and had a great time working with these students.
Thanks, Victoria. Next up is Bailey. I think Bailey wasn't able to join right now. And finally, we have Shreya.
Hello, everyone. My name is Shreya, and I'm an incoming freshman at the University of Illinois at Urbana-Champaign. And I'm so excited to see the students' final presentation because they've worked so hard this entire month.
Yeah, thanks so much. And so for the final event, students are holding a press conference documenting their response to a simulated hurricane in the New England area. The team is broken into 4 teams: planning, logistics, operations, and public information. Each team is responsible for handling a different part of the response, from forecasting, evacuations, managing supply routes, providing situational awareness, and informing the public of the state of the response. These tasks showcase the many different skills that they've learned over this last month. And without further ado, I'm very excited to present the 2021 BWSI Remote Sensing for Disaster Response final presentation. Over to you, students.
Welcome, everyone. Able to see my screen?
Okay, yes.
Okay.
Welcome, everyone, to the Hurricane El Jefe press conference. We are part of the BWSI Remote Sensing for Disaster Response 2021 program, and we'll be taking you through our journey of counteracting this dangerous hurricane. Here is our public information team. So in class this month, we always ask a question, what is remote sensing? Well, remote sensing is using imagery and data to create an appropriate plan during a disaster and to aid decision-making during disaster response. This course was driven by Python. We retrieved data from satellites. Some of the satellites we used are Landsat-A and Sentinel-2, and we use Python analysis to make sense of the data. So what went into dealing with Hurricane El Jefe? So for our final project in this program, we were given a theoretical disaster situation that we needed to prepare for and organize. The disaster was an incoming hurricane, which we named El Jefe. As the situation unfolded, we were given more information. So here's a day-by-day breakdown of what we did in response, starting with the weather forecast for day 1.
The weather over the mainland is good right now because the hurricane is currently over the Atlantic. It is forecasted that there will be winds between 70 to 105 miles per hour. There are high levels of precipitation in the Atlantic, so we forecast that there will be high levels of precipitation when the hurricane touches down. And now we will be moving on to Tejas, who will be explaining an overview of the projections, analysis, and evacuation in shelter zones.
Hey everyone, my name's Tejas. I was the liaison to the planning team. So as we can see in front of us, we have the initial storm path model and cone of uncertainty for Hurricane El Jefe. The cone of uncertainty represents the probable track of the center of the storm over the course of the day. As of 8 a.m. on Wednesday morning, we see that wind speeds are expected to be between 70 to 79 miles per hour off the coast of Massachusetts, while as we approach the mainland East Coast later in the week, we see that the wind speeds get up to almost 100 miles per hour, making El Jefe a Category 2 hurricane. Predictions for Saturday and Sunday are shown by the region in blue, but these are still prone to more errors given that the center of the hurricane could move anywhere in the region, which is why it's called the cone of uncertainty. So as we can see here, we have a blurred projection of the hurricane path. This blurring is done on purpose to better show us the possible areas that could be affected by the hurricane. As we can see, as the hurricane progresses towards the northeast, we have more and more possible deviations that the hurricane can take, represented by these different bars, showing the amount of uncertainty that the future holds. To better understand the region we are working with, we made a population density map of the region to see where people are highly clustered and therefore more vulnerable. Based on the map, where yellowish colors are low density and more purplish colors are higher density, the Cambridge and Boston region has the highest population density in the region, given over here and over here. And this is like the Connecticut area. This alongside the digital elevation map will help us figure out which areas are most vulnerable to flooding. This information will allow us to understand which areas need the most aid or need to be evacuated. Alongside the population density map, having a digital elevation map, abbreviated DEM, allows us to figure out which areas are most vulnerable to flooding. On the left, we see the region where the DEM is projected enclosed in a purple box on the map. In the middle, we see that lighter colors, such as those in yellow and green, are representing higher elevations, while those in darker colors, such as blue or purple, are representing lower elevations. Areas with lower elevations are more prone to risk from flooding from the hurricane and therefore should be evacuated or warned. Next, we will be discussing the Social Vulnerability Index model. This model uses socioeconomic data to identify the most vulnerable communities. Darker colors, such as green and purple, represent higher vulnerability, while lighter colors, such as those in yellow, represent lower vulnerability. Vulnerable communities would be less able to endure damage from the hurricane and are therefore a primary target for first responders and for evacuations. So, what are we doing to stop this hurricane? In preparation for Hurricane El Jefe, the states of Massachusetts, Connecticut, Rhode Island, New Hampshire, Vermont, and Maine have set up state, regional, and federal measures to counteract this hurricane. Working with FEMA, each state's emergency management forces have determined ways in which the people can stay safe, what zones need to be evacuated, and where each safe house is located. Through this coordinated response, they hope that they'll be able to get these states through the hurricane with minimal harm. And now we'll move on to Sarah for how you can stay safe during the hurricane.
Here's how you can stay safe in the hurricane. If you're within the target area of the hurricane, please evacuate. If you're around the target area, then do the following. Watch and listen to the news and stay updated. Use a TV and or a radio. Do not go outside until you hear an official message saying you can. Go into the interior room or a downstairs bathroom and stay away from windows and glass doors. Also, have an emergency supplies kit that includes flashlights, batteries, 3 days worth of water and food, a first aid kit, cell phone and charger, blankets, and 2 days worth of clothes.
Thank you, Sarah. So now we're moving on to the evacuation zones, as Sarah discussed. So the most affected regions are labeled with these gray polygons, as you can see on the map, and these are what we deem evacuation zones. So as we can see, most of the coastal regions are bearing the brunt of the hurricane and should be evacuated. So if you're in these zones, it is highly recommended that you evacuate soon so that you can stay safe. And here are the shelter zones and safe areas you can go to if you're able to. Each of these will be equipped with and receive regular shipments of food, water, and medicine for the duration of the hurricane. And these are coordinated with state and national emergency management forces for the best protection of you all. So now let's hand things over to the planning team for a bit, who will be walking through with us more about the information regarding projections, how they arrived at each of the models, evacuation zones and shelters, and what processes they used. They've been kind enough to come to this conference to speak with us, and to kick things off, we will be playing a short introduction video.
Hi, my name is Mark, and I'm part of the remote sensing planning team. So far for the group, I've helped create a few types of maps, the main of which is the cone of uncertainty, which pretty much just maps out where the hurricane will be at each specific time frame and also what the average projected wind speeds will be at these time frames. The map also includes the overall path that the hurricane should take throughout the course of New England.
Hi, I'm Jenny. I'm part of the planning team, and I'm working on the flood depth map to determine regions that are likely to be flooded when the hurricane hits. So this is useful for helping to predict regions that should be evacuated and where the shelters should be.
Hi, I'm Mark, and I'm on the planning team for the remote sensing course. I'm working on tracking hospitals and clinics that are out of flooded areas using geodata frames and flood maps. And these hospitals and clinics can ultimately provide medical resources to those who had to evacuate the flooding or hurricane.
Yeah, I'm Anna, and I'm part of the planning team. So basically what I've been doing is creating a population density map and a social vulnerability index to help my team see which locations or areas might need more resource allocation or evacuation centers.
Hi, I'm Aviva, and I'm on the planning team. I've been looking at data for potential shelter locations in the area that we could evacuate people to. I also looked at capacity data for each one, so we can figure out exactly who goes where and how many shelters we'll need.
Hi, my name is Shadula, and I'm a part of the planning team. I worked on helping my team create a flood depth map to assess the levels of storm surge by calculating the severity based on the area's distance from the hurricane center. I also worked on creating a wind map based on the projected path of the hurricane center, which was found by averaging the possible latitude and longitude points of where the hurricane would go, and this was used to determine the types of winds in a given location. This helped determine the severity of the effects of the hurricane at certain locations, which helped make evacuation and sheltering plans.
Hi everyone, my name is Samson, and I am part of BWSI Remote Sensing's planning team. For this simulated hurricane response, I mostly focused on using satellite imagery, specifically those from Landsat 8, to create a map of soil moisture, which when combined with digital elevation model, can be used to more accurately determine which areas will flood first in the event of a hurricane. I also used image processing techniques to fine-tune the results to make the regions more identifiable. This data can then be later used by other members to prepare evacuation routes to most safely and efficiently evacuate people from the disaster zones.
All right, so let's give a warm welcome to the planning team.
All right, so I'm Aaron, and I made the cone of uncertainty. So the first thing that I had to do was import all of the forecast data that was given to us. The next thing I did was I grouped all of the data by their date and time that they were collected, and I found the area of each point of data inside each data frame, including the max winds, latitude, and longitude. The next thing I did was I created tuples of each of the latitudes and longitudes in order to make points on the map. I then converted these to buffer points, meaning it's pretty much just a point with a radius around it to make it appear larger. The next thing I did was I joined each consecutive point with each other, And then I took those, the first 5 join points, and I turned it into one large polygon. And I did that for the last 2 as well to show the difference between the first few days and then the last 2. The next thing I did was I plotted each of the final join pieces over a base map of the area to show where the hurricane should hit. I also added labels at each of the points and color coded them with respect to their wind speeds. The next type of map I did was the hurricane path likelihood map. For this one, I wrote the code that took each of the paths and mapped them out in a buffered fashion so that they all overlapped with each other, and it showed the darker regions being more likely to be hit and be hit harder.
So the next step to predict where the hurricane will hit the hardest is to calculate the projected hurricane center path. And to find this path, we used all the possible points from the day 1 forecast and found the mean of the values based on the forecast hour. So finding the averages of the longitude and latitude values just made it easier to approximate where the hurricane will hit next. And here on the figure on the right, we can see the plotted points show the general direction of where it will go, which gives us a rough overview to carry out our next calculations. So the next step in assessing the damage that a hurricane does on a specific area is creating the wind map. And this map shows the various levels of winds there are according to severity. In the red, which is a 50-mile radius from the hurricane center, we have the hurricane force winds. These are the strongest winds and tell us that we need to evacuate these areas immediately. In the orange, which is a 100-mile radius from the center, we have the strong tropical storm winds, which are less severe but can still cause danger in certain areas, especially when combined with flooding. And finally, in the yellow, which is a 200-mile radius from the center, these are the tropical storm winds, and they are the least dangerous of the winds, but still cannot be taken lightly. So here we have some of the code we wrote to generate the wind map, and just to give a brief overview of what we did, we basically just calculated the points a certain radius away from the hurricane center, or the winds will be strongest, to know exactly where the winds will be strongest, which will be one of the major factors in planning the evacuation zones. So we just combined all the different points in different directions into polygons, and this generated a path to show us where to watch out for winds, and it was just an approximate model.
Okay, so we created a flood map based on elevation. This map is used for flood projections, and each blue point represents a location that are likely to experience flooding. As can be seen, the flooded regions are mostly concentrated around the coast, and this information, along with the wind map, allow us to make evacuation plans because we can predict where the damages are going to be. So to further analyze the effect of flooding, we zoomed in on the digital elevation map of 2 coastal cities, Boston and Portland. The maps to the right are bathtub models, which are maps that predict what the region will look like when seawater rises. So in order to do this, we took the elevations from the digital elevation map and subtracted each point by the water height. The places of a negative elevation will then be set to 0 and appear as dark purple because they are basically underwater. Since Boston and Portland are both within the hurricane force wind region, storm surge will be about 5 to 6 meters. And for the bathtub models, we illustrated what the cities will look like when the seawater rises 6 meters.
So next we have the soil moisture map, which I used data from Landsat 8. And so on the picture on the left, the regions in white, they represent areas with higher soil moistures, which means they are more likely to be flooded in the event of a hurricane because the soil can't absorb as much moisture. When this map is combined with the digital elevation model and a social vulnerability index, they can be used to more accurately determine the evacuation zones.
So then we graphed the flooding risk analysis, which essentially shows which areas are at highest risk due to flood damage, so are more likely to need resources and assistance. We graphed this by multiplying the flood map by the social vulnerability index data. The lighter colors show the less impacted, while the darker colors will be more impacted. So the image on the right shows a snippet of the process data used to map the flooding risk analysis. As you can see, it shows the state, county, and specific coordinate location. The DN represents the likelihood of flooding, and the RPL themes show the social vulnerability. The column labeled flooding, which is the value being graphed on the map, is the product of the DN and RPL columns. So taking into account the previous map analyses, including the flood map, wind map, and SVI, we determined the appropriate evacuation zones, which will be used by the people being affected by Hurricane El Jefe. This data is graphed using polygons, and each row corresponds with each evacuation zone.
So we had to look at potential storm shelters that people in evacuation zones could go to. So these included schools, community centers, and stadiums or convention centers. So there's all the potential shelters in the area mapped out in that map, but we won't need all of them for one storm. So first we had to filter out shelters that were inside evacuation zones because these would not be safe to go to. Next slide. So in the map on the left, the shelters inside evacuation zones have been filtered out. And then on the right, the shelters that are closest to people who need to be evacuated are singled out. So transportation time is minimized.
So using US hospital data and removing those outside the bounds of the grid, we were able to determine the hospitals in the area, which are shown in the blue as the blue dots in the plot. And then these hospitals and clinics can provide medical supplies to those affected by the flooding and high wind zones.
Thank you guys so much for that wonderful presentation. I just have a couple of follow-up questions for you guys, if you guys don't mind. So my first one is, like, what difficulties did you guys run into throughout your process of working through this hurricane response?
Yeah, so we did run into, I think one main difficulty was that, the process was a bit inefficient because it wasn't necessarily something that was anyone's fault, but a lot of our tasks relied on each other. So for example, we had to find which zone to evacuate and which shelters we could use. But to do so, we needed the flood and wind maps. So when we did run into issues with those, like for example, there was an issue downloading the data because there was a large amount of files, it kind of slowed down the whole process. And we also found that many other teams relied on us, like the operations and logistics teams, because they needed our evacuation zones. So I feel like that was like the one thing was that some of the things were happening kind of chronologically instead of simultaneously.
All right, thank you. My second question would be, why is it important for maps to widen throughout the course of the hurricane's path?
Yeah, I can take this one. So the path needs to widen out to show the uncertainty of the path. So it's easy to tell where the hurricane will be in a few hours, but all of the possible paths begin to diverge as time goes on. So we need to make the path widen to account for all of the possible paths.
Ah, that makes sense. So a third question that I have is just, where did you get your data? It's just a general question.
Yeah, so to determine hospitals in the area, I used the CSV file with US hospital data and then converted that to a data frame, which allowed me to see which hospitals were in the New England area.
So for the shelter data, I use this platform called Homeland Infrastructure Foundation level data, which has lots of open data on the whole country, especially for emergency management. And it actually had a data set of potential shelters in the US along with each one's capacity, which was really useful.
For the satellite images, I got most of the data from USGS's Earth Explorer website. And from there, you can select a range of dates, regions, and different satellites.
Right. Interesting. So were there any noticeable patterns throughout the process that you guys found?
Yeah, I got this one. So when looking over the map of social vulnerability index and the population density, I noticed that for the most part, regions with higher population density also tends to have a higher social vulnerability index. For example, the Boston area. However, there are exceptions such as in Upper Maine, but this pattern can be explained by the extreme cold weather up north, which would cause an increase in social vulnerability index.
All right. Thank you so much, guys. Let's get a round of applause for planning team. All right, now we'll be moving on to what happened in day 2.
All right, now I have just received information about Hurricane El Jefe's forecasted storm path for day 2. As you can see, the hurricane has moved over the mainland and is now approaching its peak. There will be lots of precipitation, and there will be high wind speeds ranging from 80 to 100 miles an hour, which indicate that the hurricane is approaching Category 2.
Hello, everyone. I'm Arav, and I'm the liaison to the logistics team. So now let us move on to the logistics side of the hurricane disaster response. As you can see in this map, the 3 red dots represent the 3 ideal distribution centers in the New England area. Public airfields were selected as the distribution centers due to their ease of access and large size. The blue dots in this image represent various hospitals and shelters, which can also be used to aid in the disaster response. In this map, all the lines represent the optimized routes trucks should take to deliver disaster aid supplies effectively. These trucks are essential to help out with the aid, so the optimization of their paths was an essential problem to solve. However, there were many limitations in trying to determine these optimized routes. Some of these limitations included a fixed number of trucks, finite number of transportable resources, and a limited amount of time. So now we can move on to the logistics team so that they can explain the logistics side of the operation. Here's a quick video introducing their team.
Yeah, so hey everyone. So one of the critical areas that we need to address in order to effectively battle this hurricane is the placement of distribution centers. So these distribution centers need to be in the right place at the right time in order to ensure that supplies and medical aid can be swiftly delivered to those who need it. So here are some of our considerations when choosing the 3 distribution centers in order of importance. So number 1 is it must be near or at airports and airfields. Secondly, it must be near large roads and highways on the game grid. Third, it must be close to areas with high population density and high social vulnerability score, or SVI. Fourth and fifth is that it must be as much as possible away from the storm path and the flood zones. So we'll be talking more in depth about each of these things shortly.
All right, so continuing off of what Akhil said, we use these factors to determine the allocation of distribution centers across the Northeast. Now to start off, as stated before, we identified public airfields as the best storage centers for pre-allocated resources, as they're large, they're accessible, and they're easy for trucks to load resources to and from. So we started by retrieving a database of all the public airfields in the country, filtering to the predicted area of the hurricane, provided by the planning team. So this gave us a data frame of all the possible airfields we can use as distribution centers. And that's what you see on the right-hand side there. We were also looking for public airfields around areas of high population, community need, and low flood risk. To do this, we compiled a set of maps, each representing something different with regards to the hurricane's trajectory.
With the help of the planning team, we retrieved a population density map, which represents the population of different counties in the Northeast. We wanted distribution centers near areas of high populations where the most people can easily receive resources. And that's what we have on the left. In addition, we needed to know the flood distribution. So there will be risk of flooding around the region the hurricane hits, and the planning team had elaborated on that before. So we needed to know what areas were least likely to be flooded or most safe from the floods, which would be an essential requirement for deciding on airfields. The flood depth map was an integral aspect of this step. The social vulnerability index was also taken into consideration, identifying communities with higher needs based on factors like disaster endurance, not limited to just population. So through an SVI data frame we retrieved and processed, we were able to use this as well to narrow down airfield locations for distribution centers. And that's the map on the right, with of course the potential distribution centers plotted. And finally, we also considered accessibility, as trucks needed to easily get to these centers, as we can see with that left-hand side map of transportation routes with the potential airfields that the rest of the team will elaborate on in a moment. And with that, I will hand it back to Akil to discuss our process and results.
Yeah, thanks, Shrevi. So as you can see here, the graph on the left is based on Social Vulnerability Index, or SVI. For those of you who don't know what SVI is, a higher SVI means that the area will be more vulnerable in a disaster. So using this graph, our hurricane response team can identify and map which communities will most likely need support. On the right, we graphed population density. So as you can see, on the left, we graphed SVI. So as you can see, the gray, the gold, and the yellow regions are higher SVI, while the turquoise, orange, and blue regions are lower SVI. On the right-hand side, we graphed based on population density. And so what do we get when we combine these two? We'll see on the next slide. So we get this graph. It's a combined graph of population density and social vulnerability index. So in order to produce this graph, I used a spatial join. And as you can see, there are specific pockets with the most vulnerability as well as population density. So what we circled here is the Boston area, the Providence area, and the New Haven area, which are all target regions or focus areas. So here, there's the most population density as well as social vulnerability index. So we needed to try our best not to place distribution centers directly on the hurricane path. So we wanted to preferably put them out west, but at the same time, we need to balance since there's a lot of high population density areas in the southeast of the map. So what we saw on the last slide, we know that our focus areas will be in the southeast region, but at the same time, we don't want to put them right on the hurricane path. So we need a bit of a balance here. So here, the thing that we can take away is the yellow lines are highways or easy access roads. So when we're choosing distribution centers, it needs to be in a place where there's easy access. So it needs to be near these yellow roads. So finally, based on all of these aforementioned factors, we can determine 3 appropriate distribution centers, as you can see on the screen. So the first image is just a game grid map with 3 locations in red dots. And the second image is a basic map with airfields, which are potential distribution centers, along with what we actually chose in red. So now I'm going to be handing it off to Alex, who's going to address more about the network optimization and routing part of our hurricane response.
Okay, so now we've chosen the distribution centers. One of our tasks is to be able to deliver supplies from these distribution centers to other locations on the affected area. So to be able to do this, we were given a map of the area in this game grid format, which you've seen before in previous slides. So what this game grid is essentially it splits the map of the area into a bunch of tiny cells, grid cells. And for each grid cell, it'll have a transport score for that cell, explaining how easy it is to travel through that area. So you might be wondering where the tiny grid cells are, but you actually can't see them because they're so small. They're essentially just all these tiny dots that form this area. So now, since we have to be able to basically perform routing, we need to be able to figure out the time it takes to travel between any two given grid cells in this game grid. And to be able to do that, we had to convert this game grid into what's called a weighted graph, which you can see on the left. So essentially, the nodes will be the individual grid cells, and edges can be thought of as roads that connect adjacent grid cells, and they'll be weighted by the time it takes to travel between those grid cells. So they're basically just roads. And the reason we have to convert it into a weighted graph is that this weighted graph will allow us to perform different algorithms, like finding shortest paths, and it'll be very helpful for routing. And on to the next slide. Yeah, so one of the issues right now is that the graph is actually huge. So there's around like 200,000 nodes right now, just because of how many grid cells there are. And this makes it really slow to do any like routing algorithms. So one of the things we can realize is that routing is only going to be done between the shelters, hospitals, and distribution centers, which there are a lot less of. So we don't actually really care about all of the other grid cells. We only need to know how to travel from one shelter to another. So we can pre-compute the shortest path between all pairs of these shelters using what's called Dijkstra's algorithm. And then after we can pre-compute all these shortest paths, that's actually all the information we need for routing. And this allows us to greatly simplify the graph from around 200,000 nodes to only 1,500 nodes, a node for each shelter and hospital. And you can see the pictures show how we can convert from this huge game grid into only these many less locations. And this will allow us to perform routing much faster, which will be explained in future slides.
Once we created a graph from the game grid, our task was to deliver supplies to over 1,500 hospitals and shelters in the New England area. We were supplied 50 trucks that started at 3 distribution centers. The total number of supplies needed across all destinations was about 2.5 million, averaging 50,000 units of supplies each truck needed to deliver, while their capacity was only 10,000 each. This means that they would have to return to the distribution centers to reload multiple times. So how do we find an efficient route to optimally utilize a few trucks to deliver supplies to all the destinations? We used a method where we essentially inched the trucks forward. We began with all the trucks split evenly among distribution centers. For each truck, we constantly kept track of its closest destination. These were all the possible next steps. We always chose the next step that would take the least time. Then we updated the next steps and repeated this process so that the trucks slowly inched forward one by one, taking the smallest, the shortest routes, and sharing the space. When a truck didn't have enough resources to help any unreached destinations, we found its nearest distribution center, reloaded it, and then continued the algorithm. There were 1,500 shelters and hospitals, so our code initially took a long time to run, which we can't have in an emergency disaster response. So we made many optimizations, like using a priority queue, to efficiently keep track of which truck had the nearest closest shelter. This algorithm turned out to be pretty efficient. Most destinations obtained resources within a day, but 2 out of the 1,500 had to wait 6 days. As you can see on the map, there are many paths, such as the bright green one in the middle, that cross over themselves, which is probably not an optimal route. The workloads of trucks are also distributed unevenly depending on the locations of the shelters. I will now hand this off to Alex, who will show our steps to optimize and balance out these routes.
One way we made our truck routes more efficient was through the 2-opt algorithm. In our case, we looked at 2 different algorithms, one that optimizes within each route and one that optimizes between routes. So our first algorithm, which looks within each route, chooses 2 nodes or points in the route and swaps the order of nodes between them. In doing this, it tries to obtain the most efficient path while minimizing intersections and loops in the route. For example, the first image on the right shows a path that intersects itself. However, by using the 2-opt algorithm, we can reduce the length of the path by reordering it. Our second algorithm performs 2-opt on multiple routes and focuses on the same strategy, which is to reduce the number of intersections and unevenness between 2 routes. Like the first algorithm, it selects breaking points between the routes, changing the order so that they're more efficient. The picture on the bottom clearly shows how the algorithm can improve the vehicle routing.
We plotted a histogram of the total time taken by each truck before and after the two-op swap. As you can see in the graph on the left, some trucks took up to 6 days to complete their routes. In the graph on the right, however, after the two-op swap, the data is significantly shifted left. Most trucks take less than a day, and all trucks take less than 5 days, while still reaching every single hospital and shelter. You can see a similar improvement in the time it took for each hospital to receive resources. In the graph on the right, after the two-opt algorithm was applied, far more hospitals received supplies in less than a day.
So thank you to the logistics team. That was really informative. Now I have some follow-up questions for your team to summarize your decision-making process. So my first question is, how did the constantly changing trajectory of the hurricane affect your process of determining distribution centers?
Yeah, I can take this one. And Autumn, that's a great question. It definitely affected our ability to effectively determine distribution centers. So every time the trajectory of the hurricane changed, so did a lot of the potential factors, specifically the flood distribution map, which we talked about earlier, which indicates the likelihood of an area being flooded based on the trajectory of the hurricane. This means that the closer the hurricane's path is to the mainland or to more land, the more risk there is for higher levels of flooding. So with the updates on the route of the hurricane, we in the planning team had to update the flood depth maps, figure out if the current distribution centers would be flooded because of the changing path. And that was definitely a challenge. But I think in the end, we chose the safest locations that were farthest from the floods. So as the daily updates came in, we were able to effectively evaluate the safety of our 3 locations. And they were successful, as we can see, in providing trucks with the resources for communities around that needed them.
Oh, that's really interesting. My second question is, how did you prioritize which factors to take into account when determining your distribution centers?
Yep, I got this one, Aura. So basically, we prioritize the factors based on first and foremost the airports. So we know that these distribution centers need a lot of supplies that need to come from outside Massachusetts, and they can be flown in only through an airport or an airfield. Additionally, the airfields can be used to, airdrop supplies or aerial rescues in flooded areas. Next up was highways, which are so important because we have numerous trucks that need to send supplies to disaster areas, and we can only do that with large roads or highways. We also wouldn't be able to send the supplies with efficiency if they are located in remote areas. Proximity to areas with high population density, high SVI, along with choosing areas away from the storm path and flood zones were also pretty important in factors in us choosing our areas.
Yeah, that makes sense. My final question is it possible that your truck routing algorithm can compute the routes, and does it have any biases in where it delivers supplies first?
Yeah, I can take this. I would say there are 2 parts to that answer. We actually designed our algorithm to have the intentional bias of prioritizing hospitals and shelters close to the distribution centers, which is good because we chose those centers to be in places with higher social vulnerability. However, there might also be unintentional biases in our algorithm. We naturally prioritize places that are quicker to get to, meaning places with better road networks, which might end up being the richer cities. If we had more time, I would definitely want to look at the per capita income of a region versus how long it took to get supplies. And if there is a bias, work on correcting it.
Okay, so there are high wind speeds between 70 or 100 or more miles per hour. There will be lots of precipitation, And the further northeast you go, the weaker the winds, and the further southwest you go, the stronger the winds. And now on to Zinnia, who will give an intro to operations on aerial imagery and machine learning.
So now that Hurricane El Jefe has hit the mainland, we need to assess what has actually happened, where the damage is, and how much damage is there. One very useful tool that we have is aerial imagery and image recognition software. Aerial imagery is images that are taken from drones or low altitude aircrafts that can tell first responders information about affected areas. It is especially useful in disaster situations when the area is otherwise impassable or hard to get to from something like flooding. Drones are a cheaper way to get imagery compared to something like helicopters, and volunteers can contribute to the effort by putting their drones into a program like Drone Responders to utilize their own drones in disaster scenarios. Once we've gathered a lot of these images, we need to have them analyzed to see what's in them. Human analysts are not very efficient and take a lot of time, so machine learning is utilized to process these images for labels like flooding or damage, which the operations team will explain in detail soon. Next slide. So imagery can also be used to create 3D models of certain areas. This is very useful when you need a more detailed or specific representation of a given area, like a destroyed building or a rubble pile. Visualizing areas can allow people to work remotely to help first responders on the ground. And now, introducing the operations team.
Yeah. So to start everyone off, I know Zenia was talking a lot about how humans can't process imagery in time. In a disaster response situation, a lot of the time we aren't able to actually send people out to survey the land, and we aren't able to get as good of a top level view as you can from like these aerial imageries. So once we've taken this data, we're able to quickly process it and provide this information to people who need it. So this might include like which roads have been destroyed by flooding, or which areas are most in need of help from disaster relief teams because they've been flooded or there's been damage there. And like these important features include communication lines, water towers, roads, bridges, anything of use that might be able to help people evacuate or for help to come in. And I want you all to imagine a situation where maybe a supply line or a disaster relief team comes in and realizes that a road might have been destroyed and they can't cross it, and that like loses them valuable hours that could have been used to save people. This is where image classification really comes into use, and it helps us identify these threats beforehand so we can plan accordingly. We're going to be using mostly airplane data, though satellites and drones can also be used. Yeah, next.
Yeah, so to get the images, we actually used LADI data, which stands for Low Altitude Disaster Imagery, and this is collected by the Civil Air Patrol. So, and this imagery came with information provided by experts about damage in any picture, environmental characteristics, type of infrastructures, and bodies of water.
So
In our project, we built a couple of machine learned models for our section. We had one to identify what kinds of infrastructure were in an image. We had one to identify what kinds of damage were in there, one to identify what kind of vehicles are in the image, and also one to identify whether or not there was flooding. These models were quote unquote multi-labeled models. Multi-labeled models or classifiers simply return multiple labels for one image at the same time. So for an example, for the model on identifying what kinds of damage were in a photo, then it might return, as you can see on the slide, in one photo, there's flooding, fire, and debris, not just one of those three labels. Next. So on a high level, here is how we built each of the multi-labeled machine learned classifiers. We used the PyTorch Python library, and from that we imported the ResNet 50, which is essentially a pre-trained a deep learning convolutional neural network, or CNN, which has already been trained to identify a greater breadth of imagery. And we used this model and we performed transfer learning, or essentially applied this model on our own data set in order to create the models that we wanted. So to do that, we created a loss and we defined a loss and an optimizer function. Loss helps identify where in the model it could improve, and where in the model weights it could improve, and the optimizer function implemented those improvements. That's in the second code snippet in the slide. And in the third code snippet, this is where we did the training. We took the model, the ResNet 50, and we fed a training data set of labeled images and then trained it for some number of epochs, applying the loss and the optimizer each time. Some more details, each of the models were trained on around 2,000 images total, each one having 4 to 7 classes.
So as we can see on the left, the model is printing out loss and accuracies as it is training. As Min said, loss represents like the error for the model to know how it's doing and to train off of. Binary accuracies represent the percent correct for each class in the multi-label. And for our final combined accuracy, we took the mean of these accuracies. As a model trains over stages called epochs, we want the loss to decrease and the accuracies to increase. I also wanted to point out a very important piece of our model on the right. Because there are many more negative examples than positive examples, we applied a weight to the loss function to reduce model bias. This small piece of code took our final test accuracies from the 50s into the 70s and even 80s.
So the first model we ran was a deep learning model to identify floods. Flood detection during Hurricane El Jefe was very crucial because we were able to identify and locate all of the areas that were flooded with an accuracy of 80%. Moreover, we were able to use that information to send disaster response units, such as Massachusetts Task Force 1, to the disaster sites much more quickly than if we had not created the model. Finally, as you can see at the bottom of the screen, the confusion matrix shows that the model identifies both floods and non-floods correctly most of the time, which means that it was a reliable source for these emergency responders.
Then we extended the flood model to include other damage classes like fire or smoke damage, debris, and node damage, all in one multi-label model. By running this model through El Jefe aftermath imagery, Task Force 1 was able to quickly decide where recovery efforts should be aimed. Combined with our other models in the upcoming slides, this also tells first responders what infrastructure is damaged and in what areas and in what damaged areas is there heavy traffic. Images like these are what the model sees and classifies. On the left, you can see obvious flooding, which the model predicted correctly. On the right, it's difficult to discern what damage there is at first glance, but zooming in reveals burned trees and debris scattered around the area. The model was able to detect both fire damage and debris, which shows that even subtle features are detected, all within one quick look at the image, hundreds of times faster than a human. Our final test accuracy was 76% after around 8 hours of training, and the confusion matrix is shown on the left. Even accounting for the uneven labels, there was a slight bias towards negative examples. One potential solution to this is adjusting the probability thresholds right before making predictions separately for each class, either manually or using an optimizer.
So the third model that we made is a machine learning model that can detect infrastructure. So this might include bridges, as seen in the pictures, roads, power grids, utility lines. There are multiple classes that we considered. So like the damage detection model, it also looked for these like minute differences between each class. As the machine learning model actually goes through each of these images, it'll look at maybe the image on the top left, and it'll see, oh, bridges have course like common features, like they're all one line, and they stand out among the environment. They're looking for all these like subtle features that can sometimes be pretty abstract, and constantly improving themselves to be able to better identify these features. Another important thing that I'd like to point out is that this model can also be used in conjunction with the damage detection and the flood detection model to actually identify damages on buildings, look if the buildings actually have floods on them. Yeah, so just the significance of adding and complementing together these models to actually produce better results. Next slide. So the total testing accuracy was around 77.5% after 8 hours of training. As you can see, here are a couple of predictions from the model. These two images to a computer would look extremely similar because they're both one white slash on a background. If you're a computer, it might be hard to look at maybe if the image on the left is actually flooding because it's surrounded by water, but it's not actually flooding. In addition, the shapes of these two are extremely similar, so it's a good sign that the model was able to predict the difference between the fact that this was a bridge and the one on the right was a road. So yeah, that was the infrastructure model.
Next, I created a multi-labeled model to identify what vehicles were in each of the photos. The specific labels the model was designed to identify were cars, trucks, boats, or no vehicles at all. Here are examples directly from the dataset. On the left image, you can see cars in the red circle. The model would return the single label car. On the right image, you can see a car in the top left corner and then a boat in the bottom right. In this case, the model would return car and boat labels. The benefit of having these models, especially in disaster response, is for search and rescue. People may be trapped in vehicles in disasters, especially in an event like flooding, and it would be good to look at an aerial image and say where potentially will there be people in need of rescue. And when used in conjunction with our disaster model, we can say, for example, in this image, there is flooding, and there's also a car and a boat potentially trapped and potentially in need of rescue. Next. So in terms of training, I trained the model for 20 epochs, which took around a full 5 hours. The full training data set that the model was trained for had around 1,000 images, with each class, the car, the boat, no vehicle, or truck having around 270 images. After training, we used a smaller testing set to test how the model performed on images not part of its training data set. And from this, we got the overall accuracy of the model, which was 71.5%. And then we use these results to generate a confusion matrix, as you can see on the right. Each matrix is for a different class like a car or truck or boat. And I've circled in red the numbers that indicated true positives and true negatives. The higher the numbers in those circles, the better the model's performance. And as you can see, the model performed pretty well, especially if you look at the car class in the top right, correctly identifying if there was a car or in an image 50 times. And as a recap step, I looked back to see what potential causes prevented the model from achieving higher accuracies. And it seems that the data set was potentially a limiting factor. There wasn't as much training data for each of these classes as there was for the damage in the infrastructure models. Next. So here are some case studies or examples of how the model performed on specific images we selected to test it. Some of these images were even from outside of the Lottie dataset. We wanted to test its performance with real-world data it had never seen before. So on the left is a hurricane aftermath. As you can see, there are a couple cars in the photo, and the model correctly predicted that there are cars there. On the right is actually an image I pulled off of Google of the Colorado floods. It's a washout, and the model correctly predicted there is a car there. Next. Here are some more examples. On the left is a hurricane aftermath with some trucks and a car in the background. The model predicted that there was both a truck and a car in there. And then on the left, on the right, the model correctly predicted that there are both boats and also cars in the image. Sorry, no, just boats in the image. So looking at the results and the overall accuracy statistic, which was 71%, we can conclude that the model is able to identify vehicles in an image, even if it is just in a tiny part of the image, as you can see in these examples, helping our first responders find out where the trapped vehicles might be.
So these deep learning models that we created were actually really helpful in the emergency response for Hurricane El Jefe. First, we used used the flood detection model to find out which areas were flooded, and we graphed those areas. Within these flooded regions, we also used the infrastructure model and the damage model to find which buildings were hit the hardest and which areas were also hit the hardest. One thing we found was that a city in northern Massachusetts was pretty badly hit by the hurricane. Among other issues was a small bridge that had collapsed and cut off access to the other side of the river. The area was also flooded, including the roads connected to the bridge. When we ran our vehicle detection model on the area, we also saw that there were luckily no cars that were on the bridge at the time of the collapse, but 2 cars on the adjacent road had been swept downstream by the floodwater and were now lying in a remote wooded area on the banks of a river. Using this information, we are able to send some search and rescue teams with the aid of Massachusetts Task Force 1 to bring the survivors to safety.
Yep, and to illustrate that, we made a small scale model of the hurricane damage. As you can see, there's water level is rising, so the buildings are being flooded. There's like debris and fallen trees and leaves in the way. Cars are underwater, and but because of our detection models, we were able to send out search and rescue teams in an efficient manner. And so this was turned into a 3D model using OpenSFM. But then in the next slide, we also used played around with other 3D modeling software such as MeshLab and Meshroom, using the structured for motion features and editing tools to create a final render. However, ultimately in the following slide, this was our final damage model from OpenSFM, and just kind of provides a little bit of a deeper view and 360 view, 3D view of the damage.
So now we have some follow-up questions for the operations team. To start off with, why did you choose to create 4 separate models rather than using one large model?
Yeah, I can take this one. So the multi-label models are grouped by damage, infrastructure, and vehicles, which are all very different. So it wouldn't make sense to classify, say, flooding versus bridges versus trucks. Also, it would be harder for a model with that many classes to converge quickly and accurately. So in a time-constrained disaster response, being slow and inaccurate is the last thing we need.
Yeah, so speaking of the accuracy, could you explain a little more about the weighting that increased the model accuracy?
Sure, I can take this one. So we were creating multi-labeled models that could assign multiple labels to a single image. For example, in an image, it could say that there's not only a car here, but also a truck. But for most of the images, they didn't contain all the possible labels. Not every image had a truck, a car, and a boat in there, mostly just a singular car or no vehicle at all. The result is that many of the images actually had more negative labels than positive labels. Positive as in there is a car here or there is a boat, negative as in there isn't a car here or there isn't a boat. So because there were so many negative labels when we initially trained the model actually was more biased towards the negative labels, and the more we trained it, the more the model realized it could just output there are no cars, there's nothing in the image in order to achieve the highest accuracy. So in order to avoid that problem, we wanted to make the positive labels in the image have a higher weight. So then the model would pay more attention to those and not just go straight to outputting pure negative labels. So that was what we implemented. We did a mathematical function that modified the loss so that the model would, the positive weights in each of the images would have a greater weight.
Yeah, all of those models are very useful. So, and for the 3D model, how does 3D modeling play a role in disaster response?
Yeah, so the 3D modeling has been helpful in predicting the potential damage and also in assessing changes occurring after the disaster. And so in an event of a hurricane, because you can't be in that situation because of the dangerous conditions, it helps provide a kind of a remote view and understand the relationships and space between 3D objects like buildings, so you can then act accordingly.
Yeah, and as a team, what were some of the biggest challenges that you faced throughout this process?
Yeah, so one of the biggest things is as the machine learning model actually trains, because of the data that we give it, it always develops some preconceived notions. So I'll give a couple examples. So maybe in our data set, all the roads and all the bridges and all the buildings were always in the center of the image. Or maybe all the bridges were always a certain color. Then the machine learning model would actually develop these certain biases that we don't want it to develop, like, oh, all bridges are gray, or all the buildings are always in the center of the image. So we had to work to actually make sure that the machine learning model actually didn't develop these biases, um, which when used in a real life situation might not work as well. And when like considering these things, we also have to consider that it takes a lot of time to train the models. Like for the models that took in 2,000 images, like it took around like half an hour just to go through the entire set just once, and we have to do that like dozens of times in order to get an accurate model. So we needed to make sure that we had everything right before we started running something for like a couple hours. Yeah.
Yeah, thank you, operations team. And now back to Noah for the weather.
The hurricane is now moving east and leaving the New England area. The far northeast will experience winds from 70 to 80 miles per hour, which shows that El Jefe is in between a tropical storm and a Category 1 hurricane. There will still be precipitation in the area, but we can safely say the worst is behind us.
Thank you so much, and we're ready for any questions that you may have.
Great, thanks. The audience had some very interesting questions. For the planning team, how do you determine what is an acceptable margin of error when determining hurricane path margins?
Well, I can answer this one. So the margin of error it kind of progresses as we move throughout the day. So through day one, we had a certain amount of forecast that we were given. So something that we could have worked on more, I think, was using all those forecasts. Like what I did was do an average of all the hurricane paths to create one so I could make the wind map around it. But instead, we could have used each individual forecast and overlapped all the wind maps to create a more accurate wind map. So I think that was like one way we could have improved that.
Cool. And let's see, also for the planning team, how is social vulnerability index determined? What factors affect it?
I can answer this one. The social vulnerability index is taken from the CDC, and I believe it's calculated using the US Census data, and it takes into account factors like housing, transportation, and socioeconomic status.
Cool. One question for the logistics team. How did you guys decide to use the inch forward method?
Well, we considered a lot of options. Another option we considered was calculating the routes of each truck separately. Like first we would calculate the first truck, then the second truck, but we figured that would make a lot of trucks intrude onto each other's paths, and the best idea was to spread out the work between the trucks. So the inch forward method was chosen because it would mean that each truck considered all of the other trucks' potential paths before making a decision. So that way the work would be distributed evenly between all the trucks.
Oh, thank you. This question is for a few of the teams. How did you extract the hospital and shelter data from the game grid?
I guess I can answer this one. So basically we were given like a huge data frame with all of the shelters and hospitals, and they'd give us like their locations. So to find where they were on the game grid, basically we performed a spatial join between the hospitals and the game grid, and it would find all of the basically grid cells that each hospital was in.
Cool, thanks. For the operations team, can you elaborate a little bit more? One of the slides regarded a bias to negative examples. Could you elaborate as to what would lead to a bias in those images?
I can do this one. So when we had our data set in the first place, the data set itself had if you have like any image, usually there's only like one infrastructure in it. So like maybe there's only one road, and then everything else is 0, 0, 0, 0, 0. Like so like there's 0 towers, there's 0 comm lines, there's 0 utility lines, and that creates a lot of zeros in our answer or in our labels. And at some point, the model itself will start thinking like, oh, when in doubt, just choose 0 because it's probably not there. And that's something that we didn't want to see. So what we did instead is we gave any like positives. So like if there was indeed a road there on the label, then we would give that more importance. So we would artificially increase the importance of that like that feature or like that positive in order to make up for the fact that there's so many negatives, and that balance the model.
Thank you. So remote sensing for disaster response is undoubtedly a collaborative process. And for all the teams, how did you guys pass information between the teams? How did you work that out?
I can take this question. Basically, what we did is, as the public relations team, we basically had liaisons to each of the different teams. For example, I was the planning team liaison, Xenia was the operations team liaison, and Arav was the logistics team liaison. So basically, we worked with each of the teams to get the information that we needed, and then each team within themselves would also pass along information to see like let's say logistics team would be like, planning team, we need this evacuation map so we can get the trucking routes, and then planning team would work on that first, so then logistics team can work on the trucking routes. So basically we had like a list of priorities that people would work through, and that's basically how we passed along information.
Oh, thank you. For all the teams, a lot of the teams said they used Python in order to map their data. How exactly was the data mapped with Python? What tools were utilized in Python, and how did Python go about mapping all the data you guys showed?
I can take this question, and that is definitely a great question. Python was the predominant language we used, and for a platform, we used Jupyter Notebook. Now, this is really helpful because it allowed us to test different models without having to run all the code. As you saw in a lot of the teams, for example, with the operations team, training the model with all of those resources required 5 hours, which I'm sure we would not be able to run multiple times just to test one model. So this was the platform we used so that we could run chunks of our code, test it out, modify it in order to make sure that we were putting out the safest plan for this hurricane. So we did use a lot of modules or libraries, which are these pre-built list of methods in Python that allow us to conduct certain functions. For example, with plotting the maps that you saw, especially on the planning team side, we use matplotlib, which is a really useful source for taking a set of data and plotting it in a lot of different ways, a scatter plot, a histogram, just visualizing the data. So we did a lot of geographic data as well, as you saw plotting on maps, which also used its own set of data. So we got Landsat 8, which is, I believe, something that the operations team talked about. That was a really good source for a lot of our data. Now, this is a remote sensing course, so we did use a lot of different modules and libraries like this, but it is important to note that all of the maps that we plotted, all of the visuals that you guys were able to see today, that was a whole bunch of collaboration and data analysis. So being able to take a data frame, I did use the word data a lot, taking a data frame with a lot of information, and being able to condense it, being able to figure out, okay, what's the information we need in order to map all the possible airfields in the Massachusetts area, or map the social vulnerability index of the Connecticut area. That required really advanced training into being able to identify what type of information you need using methods like masking and filtering out rows or columns that are unnecessary. And ultimately, this was definitely a really good experience to let us know how to use this data, how to visualize it, and how to create this plan that we presented to you guys today.
All right. Thank you, everyone. That brings us just under the wire. Thank you so much. And this will conclude the Remote Sensing for Disaster Response 2021. Thank you.